Hello everyone, my name is Ming Chang. I'm about first year student studying physics and atmospheric science. Today our topic is steady-state electron transport, including electric field. Basically what I'm doing in this summer is apply voltage to a material with infinity lengths and to understand how much current flows. The figure on the right, it is a plot of current versus voltage. The black line is linear region, the blue line is non-linear region. Our project is to focus on nonlinear transport properties, and there's a lot of applications connecting with. For example, nanoscale devices or so-called power devices. However, it is hard to solve this type of applications since you will need to solve Boltzmann transport equation using Monte Carlo simulation. Our goal is to show there's a method that can obtain same answer or very close answer at a fraction of computational cost, and this method is Shockley Flux. It is much simpler theory compared to Boltzmann transport equations, and also a simpler theory means you can get physical insight easier from that theory. Shockley Flux method is basically two ordinary differential equations. In the content, flux is number of carrier times their velocity, and where F plus is forward electron flux, F minus is backward electron flux. Lambda is mean free path with energy dependent. M is distribution of modes, which is also energy dependent. E is electron charge. Epsilon is electric field. Theta here is the step functions. If electric field is positive, in here theta will be equal to 1, otherwise it will be 0. In here, if electric field is negative, theta will be equal to 1, otherwise it will be 0. Look at the picture here. This line, the bottom line here, is potential barrier for electron charge. Everything above this line is like states in conduction bands. Everything below this line is like band gap, which no state will exist under this line. This is right contact, and this is left contact of the material. We are injecting electrons on the left contact. In here, the black arrow represents the deceleration term in the equations. In the picture, electric field is negative, so only F minus will be left, which only backward electron flux will be decelerated, and forward electron will be accelerated, which makes sense since electrons move in opposite direction of electric field. In here, F plus is increasing, F minus is decreasing, and when it hits the barrier, it will return. However, there's a probability for electron to scattering itself. The red arrow shows the direction of electron after its scattering. It represents the scattering terms in the equations. On the end of the two sides are boundary conditions, which we know exactly all the injected flux looks like from the content. Mercalli-Shockley flux are control what's inside the material. Overall, you can solve the equation. You cannot solve the equation by hands, so you will need to solve it numerically using discretized method and write them into computer language to solve the problem. While solving the problem, we assume our module is, or semiconductor is parabolic band module, and we assume that mean free path is in power law. These two figures are two important results that I got in this summer. The first figure is deviation of forward flux and backward flux in one electric field. you can see how flux flows inside a material. The integral of first figure with respect to energy is 1 point on the second figure. The second figure is net flux versus electric field, where you can see net flux decrease exponentially as electric field increase. Thank you for your listening.